Welcome everyone. We are going to consider in this lecture input-output linearization, and by that I mean if we have a differential equation that relates the output of the system to its input, then we are going to use the input to linearize that equation, and consequently we can set the dynamics using control design the way we like. The model we are going to consider will be composed of two equations, the state variable equations and the output equation. The state variable equation will include x as a state vector, and x is composed of x dot up to the nth minus 1 derivative of x. F and g are normally called in the literature vector fields, and these are vectors. Each element of that vector is actually a nonlinear map, which maps a subdomain D in the real space of dimension n. And that mapping is from D to the real space R of dimension n, as in the case of F. And in case of G, it is a mapping to the real space of dimension n by 1. And that means that we are considering a single input system. So here we have single input. So U is of dimension 1. H is also a mapping from D to the real space of dimension 1, and that means that we are considering single output system. Of course, this analysis can be generalized to include multi-input, multi-output systems, but for simplicity here we are just considering the case of a single input, single output system. Now, when we design feedback linearization based on the output equation, we take the derivatives of the output equation y, and we continue taking the derivative until u appears in the differential equation, and then we design the controller. Now, there are two possible cases that we could face. The first case is when we have to take the derivatives up to the order of the system, which means in our case here we'll take the n derivatives of y till we have u appear, and in that case we call the system of relative degree equals to n, and that's what we are going to consider first. The second case is when we have u appearing in the input-output differential equation just after some r derivatives which is less than n. In that case, we will consider the design separately. So let's take the case where we have a relative degree equal to n. If we define psi1 as y, which is h of x, then the first derivative of psi is y dot, and that would be the partial derivative of h with respect to x times x dot, and we substitute for x dot from the original state variable equation, so that would be f of x plus the partial derivative of h with respect to x times g times u. But since we agreed from the beginning that the system has a relative degree n, that means that this component in the expression of psi dot is equal to 0, and we define that as psi 2. So we take the second derivative of y, which is psi 2 dot, and that will be equal to the partial derivative of psi 2 by x times x dot, and again we will substitute for x dot from the original system equation, but since g times the partial derivative of psi by x will be equal to 0, since the system relative degree is n, then we will end up having an expression like that. So it's the partial derivative of psi 2 with respect to x times f of x, and again we define that as psi 3. We continue this process till psi n minus 1 dot, and that will correspond to the nth minus 1 derivative of y, and that would be the partial derivative of psi n minus 1 by x times f of x, and that will give psi n. The derivative of that, of psi n dot, that will give us the partial derivative of psi n partial x times f plus the partial derivative of psi n x times g times u, and in this case, of course, u appears in the last equation. So this way we can actually write the state space model in the form, say z dot equals the A matrix in the controllability form times z plus the controllability form of the B vector times V, where V is the expression that we have derived from psi n dot. We can define the vector z as psi 1, psi 2 up to psi n transpose, and the A matrix, this is the controllability form of the state matrix. So we'll have here column of zeros. Here we'll have the identity matrix of dimension n minus 1, and the last row here will be all zeros. So this is the A matrix. We can also have the B vector. It is composed of all elements zeros except the last one, which is 1. Now, of course, we can, if we would like to design a controller, we can set V, say, equals to minus K transpose Z, and consequently you can specify the required dynamics of the linearized model. And of course we know the relation between U and V, so once we find V, we can go back and calculate the corresponding value of V. Now this system is a system of relative degree n, which means that there is no internal dynamics to study, and that also means that if we have a certain equilibrium point and we do the design for that model based on the equilibrium point, then we can stabilize the equilibrium point using the controller as we have shown here. Now let's see an example to illustrate the implementation of that idea. Suppose that we have a second order system. We have here two first order differential equations to represent the state variables for x1 dot and x2 dot, and the output equation as y equals to x1. Now we can take the derivative of y, so that would give me x1 dot, and consequently x1 dot is x2. So u doesn't appear here in this equation, so that we have to take a second derivative of y. So if we take y double dot, that would be x2 dot, and we can substitute from the equation of x2 dot, and in that case u will appear. So we can see here that the input-output differential equation of y double dot has u appearing in it, and consequently we can conclude that this system is of relative degree equal to 2, and since it is a second order system, then actually n is equal to r, the relative degree equal to 2. We can select v here as equal to the right hand side of the equation for y double dot, and if we define psi 1 to be equal to y and psi 2 to be equal to y dot, then we can write the state variable equations as psi1 dot, which is actually x2 or psi2 as equal 0 1 here, multiplying the psi1 and psi2 vector, and psi2 dot, and that would be equal to v as we agreed. So we'll have here 2 zeros and 1 in the last element, that multiplies v, and the output is psi1. Now if we take a different choice for the output, like for example if we select y to be x2 rather than x1, then if we take the first derivative of y, which is y dot, that would be x2 dot. If we do that, we will find that u will appear in the equation for y dot, and that means that the system would have a relative degree 1. So this example shows that it is a sim physical model, which is actually the Denver pole equation. By a specific choice, we could have a relative degree equal to 2, as we have done in the example here, and if we take y as x2, the relative degree will be just 1. And in that case, of course, we will have internal dynamics that have to be studied. Another simple example to illustrate the choice of the effect of choosing the output, if we consider this second order system where x1 dot equal to x1, x2 dot equal to x2 plus u, and we take the output y to be x1. If we take the first derivative of y, it will be x1 dot, and that will give me x1. And if we take the second derivative, like y double dot, that will give me again x1 dot, which is x1. And this will be endless. So if we take even up to the nth derivative of y, we will still get x1, and u will never appear in the equation of the system. And this is a very special case where a system doesn't have a well-defined relative degree. So this could occur as well. So that actually is what we wanted to say about the case where we study a system with a possible relative degree equal to n, and now we will talk about the case when the relative degree is less than the full order of the system. So let us consider again a state variable equation, x dot equals f of x plus g of x times u, where x is the state variable vector, which is composed of n components, x1, x2 up till xn. F and G are vector fields, and they are vectors. Each component of that vector is a map from a subdomain in the real space to the R to the dimension n. U is a single input signal, and we take h of x as the output y. We define that as psi1. We assume that h is a smooth function which is continuous, and we can take derivatives of it. So in order to find the input-output differential equation of the system, we calculate psi1 dot, which is y dot, and that would be the partial derivative of h with respect to x times x dot, and that will give us the partial derivative of h with respect to x times f of x. We define that as psi2. Of course, we are assuming here that the relative degree is greater than 1. That's why the term of partial h, partial x times g doesn't appear in this equation. And we can continue that, say to, if we calculate the derivative of psi r minus 1, that would be the derivative of the r minus 1 derivative of y. That would be the partial derivative of the partial derivative of psi r minus 1 with respect to x times f of x, and we define that as psi r. And since the relative degree is assumed to be r, then the derivative of psi r would be the partial derivative of psi r with respect to x times f of x plus the partial derivative of psi r with respect to x times g x times u, and that's what we define as v. So now we can write the state variable equations that represent the variables psi 1 up to psi r. I'm going to define a vector zeta, which is composed of psi 1, psi 2 up till psi r. In that case, I can write that zeta dot would be equal to the A matrix in the controllability form times zeta plus the B vector in the controllability form times V. And of course, the matrix A will take the usual form. Have here column of zeros. Here I will have identity matrix of dimension r minus 1 times r minus 1. And here at the bottom I'll have 0 vector. So this is A. B will be composed of all 0 elements except the last element, which is 1. Since the system has a relative degree r and that's less than n, that means that we have internal dynamics of order n minus r. So I'm going to define a vector eta, which is composed of n minus r components. I will call these components phi. So phi 1, phi 2 up till phi n minus r. And these components will represent the transformation from the x domain to the new transformed domain, and we will see how to find these expressions. In order to do that, let us recall that eta dot is the partial derivative of eta with respect to x times x dot, and x dot is f of x plus g of x times u. But since I'm assuming that these are internal dynamics, that means the product of the partial derivative of eta with respect to x times g has to be equal to 0. So the condition that this new transformation functions have to satisfy is that the partial derivative of this transformation with respect to x times g should be equal to 0. Now I know that eta is composed of phi 1 up to phi n minus r, so each element of this vector has to satisfy that condition. So I will reach to the condition that the partial derivative of phi, the ith components of the vector eta with respect to x times g of x, that has to be equal to 0, and that's for I equal to 1 up to n minus r. So this is the actually the partial differential set of partial differential equations that we will use to find out expressions for phi. At the same time, we can also conclude that the resulting state variable equation for the new introduced variable eta would be the partial derivative of eta partial x times f of x. So that will give us the new state variable equations. So this equation for eta dot besides the equation for zeta dot, that will give me the complete state variable equations of the new system. Now, we are able to design V so that we can have certain dynamics as we require for zeta. However, we have to check whether the internal dynamics represented by eta is stable or not. And as we mentioned previously, this is difficult because the equation of eta will be actually nonlinear equation, and it is non-autonomous, and it is affected by external dynamics, which are the dynamics of zeta. So it is difficult to study the stability of this equation. Consequently, what we do is we replace that by studying the zero dynamics, and in that case, if we assume, for example, that eta dot is a function of eta and zeta, we just put zeta equal for the zero dynamics. We consider the equation eta dot equals f of eta and 0. So we study the stability of this equation, and if we find that the internal dynamics represented by this zero dynamics is stable, we can conclude that the system is locally stable. However, we can't really conclude global stability. Now we end up with a diffeomorphism that transforms the system from x to the new coordinates. Let's call the diffeomorphism t of x. That will be composed of the functions phi 1 up till phi n minus r and psi 1 up till psi r, where we define this as eta 1 up till eta n minus r and zeta 1 up till zeta r. So this will be the state variables, and I'm going to call that, say, z, the whole state variable. So the equations that describe the system would be in the form of zeta dot equals the controllability matrix A times zeta plus B times V, and eta dot equals some function of eta and zeta, and the output would be equal to C transpose times zeta, where C is has the first element equal to 1 and the other elements equal to 0. So this is the complete representation actually of our system after transformation. As I mentioned before, we can design V, so we can achieve certain dynamics for the input-output differential equation of our system. We can study the internal dynamics, specifically the zero dynamics of the system, by putting zeta equal to 0 and to find the local stability or to guarantee local stability of the system if we can show that the equation for eta dot with zeta equal to 0 is stable. Now let us see an example to illustrate how to implement the above procedure. So we have here a third order system composed of three state variable equations for x1 dot, x2 dot, x3 dot, and the output y is selected to be equal to x2. Now what we can do is to follow the previous procedure. We will define y as psi 1, and that would be x2. If we take y dot, that would be psi 1 dot, and that's x2 dot, which is x3. and we define that as psi2. Y double dot, that would be psi2 dot or x3 dot, and that would be equal to x1 x3 plus u. So here we can see that after the second derivative of the output, we have an equation that relates the output to the input. That means that the relative degree is equal to 2. The system is third order. That means that we have internal dynamics of order 1. So we have here psi1 dot equals psi2, and psi2 dot, we'll take it as v. So we can write the equation for zeta dot as 0 1 0 0 times zeta plus 0 1 times v. Here we define zeta as psi1 and psi2. We can go on to find the internal dynamics of the system. So let us take the third state to be phi, and we know that for the internal dynamics we should have the partial derivative of phi with respect to x times g of x. That has to be equal to 0, because that guarantees that the internal dynamics does not depend on the input signal u. Now what is g? G can be found here from the equation of the original system. We have here, if we write vector g from the equations here, we can write that g equals 2 plus x3 squared over 1 plus x3 squared. This is from the first equation, 0 from the second equation, and 1 from the third equation. So if we have that, we can then we know that phi is a function of x1, x2, and x3. So partial phi partial x is actually partial phi partial x1, partial phi partial x2, partial phi partial x3. So that multiplies g. So if we do the multiplication, we will get actually 2 plus x3 squared over 1 plus x3 squared partial phi partial x1. Second element corresponding to this will give us 0, and the last element would be partial phi partial x3 times 1, and that has to be equal to 0. So this is a differential equation that we have to solve. We solve it for phi, and if we do that, we will find the transformation that will complete our diffeomorphism transformation. So actually, this is solved using this expression of variables. We will assume a solution for phi in the form of f1 of x1 plus f2 of x3, and consequently the partial derivative of phi with respect to x1, that will give us the derivative of f1 with respect to x1, and the partial derivative of phi with respect to x3, that will give us df2 by dx3. So we substitute from these two equations into the equation, the partial differential equation that we wanted to solve. So that will give us 2 plus x3 squared over 1 plus x3 squared partial df1 with respect to dx1 plus equals minus df2 by dx3. Now we can assume, to solve this equation, we can assume that df1 by dx1 equal to minus 1 and df2 by dx3 equal to this fraction, and that will give us two ordinary differential equations that can be solved for x1 and x3. So we have here df1 by dx1 equal to minus 1, and that leads to f1 equals minus x1 plus some constant c1. This is the integration constant. We have also df2 by dx3 equals I will divide 2 plus x3 squared by 1 plus x3 squared. That will give me 1 plus 1 over 1 plus x3 squared, and that will give us f2 equal to x3 plus 10 minus 1 x3 plus again an integration constant. I will call that c2. So we conclude that phi then, which is equal to f1 of x1 plus f2 of x3, can be written as minus x1 plus x3 plus 10 minus 1 x3 plus c1 plus c2. We require phi of 0 to be equal to 0. That means that we require the equilibrium point, which is 0 in our original system, to be mapped to the origin of the new transformed space. So if we do that, we can conclude that C1 and C2 would be taken as zeros as well. So that will give us the transformation phi, and consequently our diffeomorphism transformation would be given by phi psi1 psi2, and that can be written as minus x1 plus x3 plus 10 minus 1 x3, and this is x2 and this is x3. So this is the transformation. Now we need to calculate the third state variable equation in the transformed space, and that's eta dot, and that will be equal to the partial derivative of phi with respect to x times f of x. And if we do the derivative of phi with respect to x, we get minus 1 0 and 1 plus 1 over 1 plus x3 squared, and that times f of x. We get f of x from the original equations of the system, and that would be minus x1 x3 and x1 times x3. So that gives x1 times 1 plus x3 times 2x3 squared over 1 plus x3 squared. Now we know that zeta 1 is x2, zeta 2 is x3, and the eta is minus x1 plus x3 plus 10 minus 1 x3, this is phi. Then we can conclude that x1 is equal to minus eta plus zeta 2 plus 10 minus 1 zeta 2. So we can write now the equation for eta dot as minus eta plus zeta 2 plus 10 minus 1 zeta 2 times 1 plus zeta 2 plus zeta 2 squared over 1 plus zeta 2 squared. And if we like to find the zero dynamics, we just put zeta equal to 0, and that will lead to eta dot equals minus eta. This is of course stable, as we can see easily from the equation. So that's how we can implement the procedure for linearizing the input-output differential equation. And that's how we can actually find the internal dynamics and consequently the zero dynamics and study the stability of the system. So that ends actually my lecture on this type of linearization. And in the coming lecture we are going to talk about the differential geometry and how we can use it to study some of the theoretical aspects of feedback linearization. Thank you.